Hi, everybody. Happy Friday. We have just a few more days of class. Today and Monday, we're going to be discussing section 9.3 of Stewart, polar coordinates. You'll have questions about this in your recitation on Tuesday. We might actually go into 9.4 on Monday as well, so you might have 9.4 questions in your recitation. And then on Wednesday and Friday of next week, we'll discuss 9.4, and then that's it. All right, polar coordinates. So part one, I just want to talk about the idea of polar coordinates. So, first of all, imagine the x-axis colored, red, green, and white. Is that colors of Italy? So red would be x greater than 0, green would be x less than 0, and white would be x equals 0. So here's the origin, and then we have the positive x-axis going out this way, and we have the negative x-axis going out this way. Okay, given an ordered pair r theta, where those can both be any real number. So they can be positive, they can be 0, they can be negative. The theta does not have to be just between 0 and 2 pi. It can be any number. So rotate the x-axis CCW. Do you all even know what that means? CCW? All right. How does it look? If you're trying out for the cheering squad and you're supposed to go CCW, what do? Oh, come on. Yeah, so you're doing this, counterclockwise, the opposite direction of the way the clocks go. So we're going to rotate the x-axis counterclockwise around the origin through an angle theta, radians. And then on this new line, put a point at the number r. So there we go. There's how we go from an ordered pair r theta to the number r. And notice that if we do that, we get an x and a y for that point. So this is the angle theta, and this is the distance r. And so notice that x over r equals cos theta. So x equals r cos theta. And similarly, y equals r sine theta. And notice by the Pythagorean theorem, x squared plus y squared equals r squared. So those equations are always true. Now, it might not look like this. I mean, r might be, might be 7 pi over 6. In that case, you'd go all over to here, and this arrow would be pointing this way. But the calculations still work. So example 1. A, given r theta equals 2 comma negative 7 pi over 6. That's the angle. So negative 7 pi over 6. Plot and find the Cartesian coordinates x, y. All right, so here we go. Here's my x-axis. Positive x-axis pointing to the right, negative x-axis green. Now we're supposed to rotate clockwise through an angle, supposed to rotate counterclockwise through an angle of negative 7 pi over 6. But that means we're going to go this way. We're going to actually go clockwise 7 pi over 6. So we're going to go around, there's pi, there's another pi over 6. This is going to be the configuration that we're going to end up with. So we're going to have our red axis going out this way, and our green axis going out this way, and there's our white point. And so this angle is negative 7 pi over 6. It's 7 pi over 6 in the counterclockwise direction. Now we're supposed to locate so we did the first thing. Now we're supposed to locate the number r on that line. Well, r is the number 2, which is a positive number, so that's out here. So this is 2 out on the red ray. So there's our point. So I plot this as r theta equals 2 negative 7 pi over 6. Now it's important now that our life gets complicated as of today because we start having things drawn on a piece of paper with an ordered pair of numbers next to them. And it's important to realize, to know, to distinguish whether you're supposed to interpret that ordered pair of numbers as xy coordinates or as r theta coordinates. So the only way to do that is to put r theta or xy next to that ordered pair. Okay, so then let's get x. The next thing is to get the Cartesian coordinates. So x is going to be r cos theta. So that's going to be 2 cos of negative 7 pi over 6. Well, the cosine of this angle is the same as the cosine of 5 pi over 6. Because this is 5 pi over 6. And that's going to be 2 times minus the cos of pi over 6. So this is going to be 2 times minus 1/2. So that's, I'm sorry, negative square root of 3 over 2. So that's minus square root of 3. You'll get to where you can do these in your head. Y is going to be r sine theta. So that's going to be 2 sine of negative 7 pi over 6. That's going to be 2 times 1/2. So that's going to be the number 1. So our xy coordinates are xy equals negative square root of 3, comma 1. So I can put that here, negative square root of 3, comma 1. But again, look, I've got 2 different ordered pairs. Those are not the same numbers. So you got to hit the reader over the head with it and say, interpret this as x, y, Cartesian coordinates. B, given x, y equals minus 1 square root of 3. Plot and find polar coordinates. Four versions. Why 4? And how so? Well, with r and theta each positive and negative. You'll see what I mean. Okay, well, here we go. Draw our axes. This is x. Oh, I should have put this over here. This is on these axes. You always want to plot now. Things get really complicated because we're drawing all sorts of graphs today. And the horizontal axis is not always x. So when it is, well, you just need to label the horizontal axis. Okay, so this means we got to go 1 to the left and radical 3 up. So there's my ordered pair, -1, radical 3. And again, we should label that with x, y to hit the reader over the head with it and tell them these are the Cartesian coordinates. All right, so how about some polar coordinates? Marcy?
Radius equals 2.
Say it again?
Radius is 2.
Good, and how'd you find that?
Because that ordered pair of xy coordinates is basically just the opposite of what you gave us in the last problem.
Yeah, and also you can do this. You know, x squared plus y squared equals r squared. So x squared plus y squared is going to be 1 plus 3. So r squared is going to be 4, so r is 2. What's an angle theta that works? Marcy, you've already done your job. Kenzie?
I'm using my hand, not to raise it.
So think about how we would have gotten here.
Oh,
Yeah?
over 3.
Well, let's try it. Here's the x-axis. Let's rotate it pi over 3. 2 pi over 3. Rotate this 2 pi over 3, and you get to there. So in that picture, r is a positive thing. So that means we're thinking of that r as that point as sitting on this red ray. Let's do another pair of polar coordinates where r is positive, because I just drew that lovely red ray and I don't have to erase it. So let's do, so this is r positive and theta positive. Let's do another version with r positive. Well, it's going to have to be positive 2. Now, so somebody else, what's an angle that will work for this that's a negative number? Liam?
-4 pi over 3.
Yeah, -4 pi over 3. So in this picture, I could have gotten here by rotating that x-axis clockwise 2 pi over 3, or counterclockwise 2 pi over 3, or clockwise 4 pi over 3. Okay, well, we're supposed to come up with notice this equation does not tell us that r is positive. This tells us that r squared equals x squared plus y squared. I don't say that r is the square root of x squared plus y squared, because that would mean that r can't be negative. But we're supposed to come up with coordinates where r is negative. Well, r is going to have to be negative 2. But let's think about our picture. Let's erase this nice red ray. Well, let's think about it. We have to have r sitting on that back ray, which has got to be green. So here we go. And it's got to be at that location. Well, that distance is 2, but it's on the back ray, so that's how we get r being negative 2. And so where's the front ray? The front ray is down here. Okay, so what's an angle, a positive angle, that would get us to that configuration? Exactly, 5 pi over 3. So if I look at this picture, I rotate 5 pi over 3 and then go out to r equals negative 2, and I'm going to get to that point. Now, what's a version where I have r negative? It's going to have to be negative 2, but I have a negative angle. On the count of 3, everybody say it. 1, 2, 3.
Negative pi over 3.
Great, negative pi over 3. Math church, you're all, this is Friday math church. All right, that's a basic intro. Meeting part 2 is polar curves. So the simplest way we get a polar curve is when r is a function of theta. R of theta. So then r comma, so r of theta, comma theta, for theta being a real number. So the set of all, I should say this, the set of all, the curve is, or the set of all, r theta, comma theta. This is polar coordinates, not x, y coordinates. For theta in the real numbers. So the set of all of those gives us a curve. So the domain is the set of all numbers, theta. And again, it'd be a lot nicer to just use t for time. Now, the thing is, that's a big domain. We think of theta being a number between 0 and 2 pi inclusive, or between 0 and 90, or between 0. We're used to these small values for angles. But in our world, we can have theta be any real number. But in a lot of cases, the r of theta function will be periodic in some way that will allow us to limit the domain. The curve will start to retrace itself in some cases. So that is, so the curve will start to retrace itself. And in those cases, we can actually consider a smaller domain. To see how the curve looks, you just go until it starts to retrace itself Look at those thetas, and then you're done. We can use a smaller domain for theta. Now that sounds kind of vague, but I'm not going to try to explain it better because I'm just going to do some examples. All right. I'm going to erase this because I want to start over here in the far left with some examples. So here's example 2 for today. A, sketch the curve r theta equals equals 3 sine theta, comma theta. That is, the function r as a function of theta equals 3 sine theta. That's the first job. Now, you should all be reading the book because there is, well, I'm always nagging you to read the book. And also, you'll notice, I always promise there's going to be something on the quiz that's an example from the book. And like the last exam on which the scores were really low, a lot of you completely bombed problems. And I circled the description of the problem that says, this is a book example. Last fall in 2301, I had a student, I remember one time before an exam, I noticed her out in the hallway. She had gone through all the sections for that exam, and she had studied every example, and she'd written them out on paper, and she had that sheaf of papers, and she was studying those examples, because one of those problems is going to be on the exam. So reading the book is valuable. It's a good book. I'm trying to prod you to do that, to read the book, by saying every quiz, every exam will have a problem that's just taken right from a book example. Okay, so in the book, they do proofs, they do curves, they sketch curves that are given in polar coordinates 2 different ways. One is they make a table of values of r and theta, and then they draw these things from that table of values. I'm going to do it the second way that they suggest. Do it so plot by first graphing r as a function of theta in the Cartesian plane. Well, that is graph r of theta versus theta. So I shouldn't have said in the Cartesian plane, because it's not. So we're going to make a graph that has theta on the horizontal axis. I'm not calling it the x-axis because it's not. It's the theta axis. And on the vertical axis, we're going to have to plot r of theta, which is 3 sine theta. All right, you're all trying out for the, you've all gone away to math boarding school, and you're trying out for the cheer squad. And your job is to do the motion that's the shape of this graph. Okay, ready? 1, 2, 3, go. Yeah. The football team's not much better. So this is going to be a sine graph. Just wiggles up and down from 0 to 3. And then it starts to repeat itself. So up to 3, down to -3. This happens at theta equals pi. This happens at theta equals 2 pi. Where does this peak happen? Pi over 4. Yes, pi over 4. You're right. No, pi over 2. You're wrong. Where does this trough happen? 3 pi over 2. So there's our graph. Now how are we going to use that to make a plot in the xy coordinate plane? Well, first of all, get out your green and your red pen. Because remember in our pictures, when r is positive, we put those numbers on that positive part of the x-axis. And when r is negative, we put those numbers on the negative part of the x-axis. Okay? So, here's our x-axis, and we're supposed to rotate this x-axis. You know, there it's not been rotated. We need to eventually rotate it through all the angles, all the way around to 2 pi. All right? Now, what's going to be happening? Well, when the angle is 0, and when the angle is pi, and when the angle is 2 pi, all those places, our point is going to be here. This is going to be r theta equals 0, 0, or also 0 comma pi, and 0, 2 pi. We're going to go through that point 3 times. We're going to start there, we're going to end there, and we're going to be there midway. Now, let's think about this. This is when the angle is sweeping from 0 to pi. So this part of the graph is telling us what's happening with r as our beam is doing this. Okay, so it's telling us r starts as 0, gets as big as 3 halfway, and then gets back down to 0. So r starts at 0, gets as big as 3 when you're halfway around, and then comes back to 0. Isn't that cool? So I'm going to plot that red part. I don't know how it looks exactly, but something like this. I don't know. So that's this red part is 0 less than t less than pi. And when you're actually at 0 or at pi, you're at this point. Now let's think about the next part of this. So when we continue sweeping the angles from pi to 2 pi, so here's the angle pi, and we're going to continue sweeping from pi to 2 pi. Now what are we going to do? We're going to put those r values on there, but those r values are green, so they're going to be on the back ray. So they're going to be on the back ray starting at 0, and then getting bigger, as big as 3, and then getting back down to 0. And they're going to be exactly like those values. So I've got another curve here, lying right on top of the other one. So the curve is one circle. The path, I forget the terminology the book uses. The path is twice around. As theta goes from 0 to 2 pi, I go 2 times around that circle. But the curve is just the circle, right? I forget the terminology the book uses. But this is from pi less than t less than 2 pi. Again, right at time t equals pi, and at 2 pi we're there. What's that look like?
Circle.
What would you say the diameter is?
1.5.
What?
No, not 1.5. 3.
Yeah, it looks like maybe it's a circle of radius of diameter 3. So it seems like it might be a circle. So the second part of this question is, get a Cartesian description. Well, if this were a circle centered at 0, what would the equation be? A circle centered at 0 has equation, yeah, x squared plus y squared equals some radius squared. It's not centered at 0, so it's not going to be that. But let's start by just computing x squared plus y squared. Let's just, So, oh, well look, oh shoot, I erased that thing. Remember that thing that I erased? It said this, x squared plus y squared equals r squared. Okay, Well, I'm going to write that as r times r. Just because I really wish I could be a pirate and I just would like to say r as many times as I can. And then I'm going to use this. What is r? R is equal to 3 sine theta. So here I've used the definition of r. Now I'm going to do a trick. I'm going to bring the 3 out front. 3 times r sine theta. Hey, but what's r sine theta? Why? Because. So this is 3y. This is the definition of y. Okay, so remember, if this were a circle centered at the origin, we'd have x squared plus y squared equals some number that's r squared. But that's not what we have, so bummer. What we've arrived at is this. X squared plus y squared equals 3y. But watch this. Let's subtract 3y from both sides. We get x squared plus y squared minus 3y equals 0. Now let's complete the square. What would I like to have added here to make this be a perfect square? Do you remember how you figure out what to add, Kinsey?
Is it 9/4?
Yeah, how do you get that?
So the middle term is going to be 2 times a times b, and a is 1 in this case, so we just need to find b.
Yeah, so you just look at that coefficient. You have it in this case because our leading coefficient is the number 1, and there's no coefficient here. So this is a very simple case. You just have that. You get 3 halves. Square. You get minus 3 halves. You square that. That gives you 9/4. But I'm going to leave that as 3 halves. Well, I'm going to do this as 9/4. That's right. Now, I can't just add that without adding it to the right side as well. So we completed the square. So why would you do that? Well, because look, this is x squared plus y minus 3 halves, that whole quantity squared of y minus 1. Yeah. And over here, 9/4 you can think of as 3 halves squared. So look, that's a circle centered at, now here I'm going to write an ordered pair, 0, 3 halves, but you got to hit the reader over the head with it. Again, your life got complicated today. You always got to say, are you speaking French or Pig Latin? So those are Cartesian coordinates with radius r equals, and I'm going to use capital R. I don't want to use the same letter R. The radius is 3 halves. So just what Marcy suspected. All right, that's example 2A. Now look at that curve, that equation you just had written down. Example B is graph or plot sketch. There are all these, sketch this curve. R equals 3 sine 2 theta. By the same method. Now, transformation of graphs. What does having the 2 inside right next to the theta, what does that do to the graph? Does it affect the y coordinates or the x coordinates? Is it a translation? Is it a multiplication? What is it? Raise your hand if you have an idea. Marcy's got a hand up. Like 25 of you in the room. I want some more hands in the air. High school, come on. This is not even pre-calc. This is algebra. What effect does that have on the graph? Mary?
Makes it taller vertically.
That would be the case if the 2 were on the outside.
Stretches it. Is it what I'm saying?
No, because it's acting on the x coordinates, or it's acting on the variable. So it affects it horizontally.
It would double the rate at which it goes through its path.
Right, which means that it's going to shrink if I want to sketch the graph. So my previous graph, I'm going to plot r of theta, which is 3 sine 2 theta. The graph that I had, which was 3 sine theta, its period was 2 pi. You had to go through an angle of 2 pi to get the thing through an entire cycle. What's the period of this graph going to be? How far is theta going to have to go for this thing to go through one whole cycle? Only from 0 to pi. So in other words, this is going to shrink the graph horizontally by a factor of 2. So instead of going out to 2 pi is over there, I'm going to go here just to pi. And I'm going to have, there's my curve. And so what's the theta coordinate here? Pi over 2. What's the theta coordinate here? Pi over 4. What's the theta coordinate here? 3 pi over 4. But it turns out, remember, we needed instructions for how to get our r as our x-axis swept all the way around. It turns out that for the second half of that sweep, the points were overlapping. But we don't know if that's going to happen. So in fact, we need instructions for the whole sweep, all the way around. So we need to continue this. Remember I said, the graph might be periodic. Here, the function r is clearly periodic. It looks like we didn't need to go this far, but we don't know how our graph is going to look. The fact that r is periodic with period 2 pi doesn't mean that that's when our graph is going to start overlapping itself. Now let's do what we did before. Let's color the positive things red, and let's color the negative things green. It's too bad we don't have a Staples, because I could say, go down to, on your Friday, get out of here and go buy yourself some colored pens. So let's make our graph. Well, first of all, notice at theta 0, pi over 2, pi, 3 pi over 2, and 2 pi, at all those times, or all those angles, we're going to be at the origin. So when we're here, 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 and here, and back to here, all those times we're going to be at r equals 0. So what's going on here? This is what's telling us with, this is r equals 3, and this is r equals negative 3. This is what's telling us about r as theta sweeps from 0 to pi over 2. R grows from 0 as high as 3 and back down to 0. So how's that going to look? As theta sweeps from 0 to pi over 2, r is going to start at 0, it's going to get as big as 3, it's going to come back down to 0. So we're going to end up with, this is awesome. This is the best reason to get a PhD in math. You get to draw pictures like this and get paid for it. We're going to get that kind of thing. Now this is r theta equals 3 comma pi over 4. That's not the xy coordinates. That's the angle of pi over 4 and r of 3. Now what happens? We continue sweeping from pi over 2 to pi. Sweeping from pi over 2 to pi. But in our r goes down to negative 3 and back up. That means we're going to be out on the back ray. So r starts at 0, gets as big as negative 3, and gets back to 0. So I'm going to color this lobe 1. This is lobe 1. And I'm going to color this green lobe 2. And that's going to be here. And it turns out then that that third lobe is going to be here. And that fourth lobe is going to be here. So we get a 4-petaled flower. 2 of them are green, 2 of them are red. And notice we did need to go all the way to 2 pi. Even though the radius function was periodic with period pi, we had to go all the way around to 2 pi to get the whole curve. So it's a 4-petaled flower. The previous picture, again, you could think of that circle as like a 2-petaled flower, but really just the petals are lying on top of each other, so you really only see 1 petal. But here you see all 4 petals. Hey, what if I changed this example C, r squared equals 3 sine 2 theta? What effect would that have? Well, if r squared is equal to 3, well, then that would mean that this r would have to be square root of 3. And this would have to be negative. Wait a second. You can't take the square root of a negative number. There is no number r such that r squared is negative. So for this example, right. So you think about in that interval, 3 sine 2 theta was a negative number. There's no r squared that's going to equal that. You can't have a positive thing equal a negative thing. So what's that going to do to our flower? It's going to pluck off. Isn't that amazing? That's really cool. You get a 2-petal flower because you lost the negative petals. All right, let's do our quiz.